In the previous lecture topic, you learned the 5 major requirements of a battery management system. And before we continue by looking at how a battery management system will meet these 5 requirements, I'd like to spend a little bit of time talking about the principle of modular design for a battery pack and how that modular battery pack design also informs and suggests a modular design for the battery management system itself. Since we're looking primarily at battery packs and battery management systems for large applications, these will usually involve batteries from which there will be a high power demand. And we know that power is equal to voltage multiplied by current, so a high power battery must deliver either high voltage or high current, or both. When we think about how to meet a high power demand, the first thing we could think about is by maximizing the voltage of the battery pack. But we find out that chemistry of individual battery cells is going to limit the maximum voltage of one cell. For example, most lithium-ion battery cells operate in a voltage range between about 3 and 4 volts, give or take. So if we require a battery pack of higher voltage, then we can accomplish that only by connecting many cells in series. And when we do so, the pack voltage is equal to the sum of the voltages of the cells connected in series. An approximate analysis would be to take the nominal voltage of one of the cells and multiply by the number of cells in series to get a nominal battery pack voltage by that. We might also consider trying to maximize the amount of current that we get from a battery pack. When we do, we find that how a particular cell is constructed places some limits on the amount of current that we can extract from that cell or put into that cell. But we also know that if we put cells in parallel, the battery pack current is divided between those parallel cells, and so that the overall pack current can be much higher even for a limited amount of cell current. And we can approximate the amount of current that we can get from a battery pack as the number of cells in parallel multiplied by the amount of current that we could extract from any particular cell. We might also be interested in thinking about the capacity of a battery pack in ampere hours. If all of the cells have equal capacity, then the capacity of the battery pack is equal to the number of cells connected in parallel multiplied by the capacity of any individual cell. And so from this, we can compute a rough but a pretty good estimate, pretty good approximation of the total pack energy and total pack power. The pack energy is equal to the cell energy multiplied by the number of cells. The cell energy is approximately equal to the cell capacity multiplied by the cell nominal voltage. So if we have NS cells connected in series and NP cells connected in parallel, the overall energy is NS multiplied by NP multiplied by cell capacity multiplied by cell nominal voltage. The individual cell power is equal to the maximum cell current multiplied by the nominal cell voltage. So the pack power is equal then to the number of cells multiplying that cell power, or NS multiplied by NP multiplied by the maximum cell current multiplied by the cell nominal voltage, at least to a first order approximation, and we'll learn more exact methods throughout this specialization. But from this approximate analysis, we can conclude that in order to meet certain energy or power requirements in a battery pack, the product of the number of cells in series and the number of cells in parallel must meet some criteria, but actually that the individual values of NS and NP are quite flexible. For example, we might find that the product for some application must be 12. In that case, NS might be 12 and NP might be 1. Or NS might be 1 and NP might be 12. Or one of them might be 3 and the other 4. Or one of them might be 2 and the other 6. So from an energy and power perspective, we have a lot of flexibility in how we choose the number of cells in series and how we choose the number of cells in parallel in order to meet these requirements. So how do we choose them? Well, the choice is usually made by economic factors and by safety factors. For safety, we usually want the overall battery pack voltage to be less than about 100 volts DC. And this factor turns out to be a little bit arbitrary. It's possible to have a safety hazard at lower voltages, or still even to be relatively safe at higher voltage, depending on the environmental conditions. So there are different professional and standards associations that come up with slightly different answers as to what is a safe DC voltage. For example, the National Fire Protection Association, the NFPA, historically had a maximum voltage limit of 50 volts DC before considering the battery to be a safety hazard, and more recently they have raised that value to 100 volts DC. Automotive manufacturers tend to be very conservative, and so they prefer to have voltages of less than 50 volts in any part of the battery pack that might be exposed. Furthermore, at this point in history, the power electronics required for operating at voltages larger than about 600 volts turn out to become quite expensive quite quickly. And for that reason, most applications require a voltage of less than 600 volts, at least at this point in time. So using both of these considerations, we tend to have limits on the number of cells that we would like to stack in series in a battery pack. So let's think about it the other way. Maybe we want low voltage, but we want high current. But there are some difficulties with this approach as well. The problem is that power losses through wiring and other components, but primarily wiring, are proportional to the square of current. That is, if the electrical current passes through wiring that has some resistance R, and the current is I, then the power loss through that wiring is I squared times R. So the bigger current is, the much faster I lose power, I waste power. So for efficiency, we would either need to reduce the resistance of the wiring, or we need to minimize the electrical current. In order to reduce resistance, we need to have far thicker wire, and we have more strands in the wiring. And the thicker it is, the more copper is required, and copper is a relatively expensive element. So we really would prefer to use thin wire, having somewhat higher resistance, in order to save on cost. So this fact tends to put design limits on the number of cells that we wire in parallel. So as we often find in engineering, there's a design trade-off. We need to make a compromise between the number of cells in series and the number of cells in parallel. A very common solution is to build battery packs from smaller modules of cells. Each one of these modules has a DC voltage that's less than approximately 100 volts in order to maintain safety of a particular module if a technician is opening the module to do some diagnostics or repair. And then you take these modules with individual voltages less than 100 volts and you wire the modules in series to make a higher voltage battery pack. And this approach overall makes the number of cells in series relatively large and the number of cells in parallel relatively small. So there still remains a high voltage hazard when we consider the overall battery pack and not just the module, but this hazard can be managed by proper care when servicing the battery pack and by putting mechanical service disconnects into the design such that when the battery pack housing is opened, it automatically disconnects the modules from each other, and so that there is no voltage inside the battery pack larger than about 100 volts when the case is open. In my experience, this is the most common approach to building a battery pack for vehicle applications. Cells tend to be wired in series more than they're wired in parallel, but there are some reasons why we might consider wiring modules in parallel as well, and we'll talk about that shortly. When we're discussing either modules that are or battery packs that are made from cells where some are in series and some are in parallel, there's a common way of talking about this. Consider the battery pack in the photograph on the right side of this slide. We see that this battery pack is made from 6 individual cells, and that these cells are wired such that pairs of cells make a module, and 3 modules are then connected in series. So overall, the number of cells in parallel is 2, and the number of cells in series, or number of modules in series, is 3. And this particular battery pack would be called a 2P3S pack, 2 cells in parallel and 3 cells in series. As a actual example, I show some photographs of components of a battery pack from a Nissan Leaf electric vehicle. On the left photograph, and on the left side of that photograph, you can see an individual battery cell, and you can see that it's a pouch format cell. And to the right side of that same photograph, you can see a module that is built from that cell. And if you open up that module, you find that it contains 4 cells internally, 2 in series and 2 in parallel. So we would call this a 2S2P module. In the right photograph, you see a cutaway of the Nissan Leaf chassis overall. And you can see that the battery pack is mounted underneath the passenger compartment of the vehicle. And the overall battery pack is built from 48 of these modules that we saw in the left photograph. And in this design, some of the modules are stacked vertically and some of them horizontally in this battery area. In addition to safety reasons, there are some other reasons why building a battery pack from smaller modules can make sense. One is that the smaller modules are easier to handle by humans or by robots who are assembling the battery. The individual modules can be tested before integrating them into the pack, and if one module turns out to have a failed component, then it's much less expensive to service that module than it would be to service an entire battery pack. Ideally, the overall battery pack design would be made from multiple instances of the same module design, and ideally the same module could be used in different battery packs for completely different applications. And the reason for this is then that your non-recurring engineering costs, your NRE, to design the battery module would be amortized over many products. The engineers need to design one module one time only and then can reuse that design for many different applications. And it's less expensive than needing to design new modules for every single new application. As we proceed through the specialization, we will consider how modular design of battery management systems is done to support a modular design of a battery pack. In particular, we will tend to focus on design extremes, but the methods that you will learn are general and apply to designs even in between these extremes. So suppose that I determine that I need 3 cells in parallel in a battery pack and 96 cells in series overall. I might consider then the design shown in this drawing that you see on the slide. In this drawing, we take 3 individual cells and we join them together in parallel to make a module. And that module we call a parallel cell module, or PCM, because its cells are connected in parallel. And then we take 96 of these PCMs and we connect them in series to make the overall battery pack. One advantage of this approach to a modular design is that we know that battery cells connected in parallel must maintain the same voltage just electrically, physically, because of Kirchhoff's voltage law. So we need to measure only 1 voltage per every 3 cells, which reduces the cost of my voltage sensing and some of the battery management algorithms as well. And for the same reason, the individual cells inside of one of these PCMs will self-equalize or self-balance because they must maintain the same voltage overall. And so for these reasons, it's very common to find battery packs that comprise cells connected physically in parallel before they are connected in series. But we could also consider the opposite design extreme as shown in the second illustration. It has the same number of cells and the same overall general configuration, but they are wired differently. In this case, we take 96 cells and we connect them in series to make one module called a series cell module, or SCM. And then we take 3 of the SCMs and connect them in parallel, but only at the high voltage terminals and not at the individual cell voltage terminals. there turn out to be some additional complexities to this second approach. We are required to measure the voltages of all cells, which is true in any case for lithium-ion battery management systems. But in this case, I need to measure all 3 times 96 or 288 cell voltages because they could potentially all be different, whereas in the PCM approach, we were guaranteed that each module of 3 cells had the same voltage by Kirchhoff's voltage law. Here in the second approach, they could all be different, and so we must measure them all. Also in the SCM approach, the individual cells will tend not to balance each other automatically, and so there are some additional requirements for balancing circuitry. So those are 2 disadvantages of the SCM approach. But there is one very large advantage of the SCM approach in some applications. Suppose we want to make a very large electric vehicle, maybe an electric transit bus, or maybe a large piece of heavy equipment like a bulldozer or something like that. If this vehicle must have very long range in some use cases, but relatively short range in other use cases, if I put a very large battery pack to satisfy the most difficult use case, then I've really over-designed for the simpler, lighter use case. And it would be nice to have battery packs of different sizes that I could put in a vehicle for the different use cases. But using the PCM approach, that's really not a feasible thing to do. But if I build a modular battery pack out of SCMs, then that allows me to have the same overall battery bus voltage with different capacities depending on how many SCMs I install in the application. For relatively low range, I might use 1 SCM and have a certain voltage. For much higher demand applications, I might insert 2 or 3 or more SCMs, and I have exactly the same overall bus voltage. I just am able to draw more current from it so I can drive bigger motors or bigger loads. And that means that the design of everything outside the battery pack is common, and I just plug in a certain number of SCMs, however many I need. So there's no additional design for a low capacity application versus a high capacity application. It's simply a matter of how many of these modules the consumer decides to purchase and install, and that can be a huge advantage. From our perspective in this specialization, it's possible to design battery packs and battery management systems for either one of these design extremes. And in fact, most battery packs are some combination, some compromise between these extremes. For example, we might build a battery pack from 18-cell 3P6S modules. The module and power energy are then approximately 18 times that of a single cell. Turns out to be not exactly that in practice, and we'll talk more about that later on. But if I do one of these modules with 3 cells in parallel and 6 cells in series, and then connect 16 modules in series, I come up with the overall design requirements of the application. And I meet safety limits of the overall module voltage and so forth. Well, just as I can build battery packs out of modules, I can also build battery management system electronics using a modular approach. So a modular battery pack suggests using a hierarchical master-slave battery management system design as well, and we'll talk about that on this slide and in the following slides. For example, we might have some of the electronics that are dedicated most directly to managing individual cells that are located inside of the module of cells that they manage. This design approach minimizes the wiring and the connections and the wiring losses in the overall battery pack. We would call the electronics connected directly to the cells a slave BMS, and the slave BMS has all of the electronics for measuring voltages, for measuring temperatures, and for balancing the individual cells. There's commonly a single master unit for every battery pack, and the master unit does the supervisory control of everything overall. It's directly connected to the circuitry that manages and measures the overall battery pack current and opens and closes the contactors. The master unit communicates with all of the slaves, and it can do this using a daisy chain architecture like the one drawn in the illustration on this slide. And in that case, the master talks to the first slave, and the first slave talks to the second slave, and the second slave talks to the third slave. And any response goes from one slave to the other, and finally back to the master. So there's one single bus on which everything is connected in a daisy chain kind of way. Or the master can communicate with all the slave units using a star architecture where the master is connected in kind of directly to every single slave. And there's different approaches as well. In order to reduce wiring, some kind of a bus architecture or a daisy chain architecture tends to be the most popular in my experience. In a master-slave design, the slave has certain responsibilities, and the photograph on the slide shows an example that is a demonstration board that Linear Technology has made in the past to allow designers to experiment with voltage measurement using their 6804 part. And now it's marketed under Analog Devices now that Analog and Linear have merged. This is a good example of a slave design, and you can look this up on the internet by going to the website for the 6804 part and looking up this demonstration board. It also has schematics and sample code and things like that you can work with. Even though it's a good example, it actually implements some functionality that not every slave needs to implement in practice, and so the features of this demo board could be made smaller in a physical design. One of the principal requirements of the slave board is to be able to measure the voltage of every cell in the module, and the connector on the top of the board in the photograph connects to the wiring harness that connects to each of the individual cells in the module for this purpose. Another requirement is for the slave to be able to measure temperatures, and again, there are capabilities on this example demonstration board to connect to off-board thermistors to be able to do that. From an algorithm point of view, we would love to measure the temperature of every single cell independently, but that requires an enormous amount of temperature sensors and wiring and expense. So instead, most battery packs use only 1 or 2 temperature sensors per module and some kind of an interpolation and extrapolation method to estimate the temperatures of the other cells in the module. The third function of a battery management system slave is to balance the amount of energy stored in every cell in the module. I've already mentioned balancing or equalizing a number of times, but we don't really get to study it in depth until Course 5 in this specialization. But as a preview, each individual battery cell will have slightly different efficiency from one another and slightly different self-discharge rates and so forth. And because of that, it's a requirement that we somehow be able to equalize the level of charge in individual cells, either by draining charge out of cells that have more energy than others, or by moving charge from cells having more energy to other cells that have less energy. This particular slave BMS design performs balancing by connecting a resistor in parallel to a cell that happens to have too much charge. And this extra charge drains through that resistor, and the level of charge then is depleted. And these resistors are on the top portion of this circuit board, all of the parallel components that you see there. A final important design requirement for a BMS slave is to be able to communicate all of the information that it measures and collects back to the master so that the algorithms can process this information in the master unit. And the particular solution shown here uses a serial bus where the master can communicate over a daisy chain bus to the individual addressable components or to all of the components at the same time using a broadcast message. The connectors that allow this are shown at the bottom to the left and to the right of the board, where one side has the connection from the neighboring board into this one, and then the other side connects out to the next neighbor, and finally one of them connects to the master unit. A BMS master has certain responsibilities as well. The master must control the contactors or the high current switches that connect the battery cells, the battery pack, to the load, and also disconnect the battery pack from the load. The photograph on this slide shows a prototype BMS master that we've developed in our research lab, and a production master would be much smaller and much neater than this. You must understand this is for research purposes and has different requirements. But I include this photograph to enable me to point out a few components without too much difficulty. For example, the contactors are these high current switches I've mentioned a few times. In this photo, they are in the top right portion where you see 3 white cylindrical elements, and each one of these is a contactor, and we'll discuss why we need 3 later this week. The master unit must also monitor the battery pack current, and in this particular design there are 2 approaches to do so that our research team can investigate the advantages and disadvantages of the 2 approaches. One is called a current shunt method and the other is an inductive method, and you will learn about those later this week. And both of those are connected to the thick black wiring on the bottom right side of the battery pack. The master is also responsible for measuring isolation between the high voltage battery pack and the chassis of the load, and this is also accomplished in this prototype system, although the electronics to do so are less easy to point out. They're not really obvious from this photograph. The master must communicate with the slaves, and this is done in our solution using a serial communication bus. The master must communicate with the host application, and these are done by, again, some communication buses that are connected with some of the ribbon cables that you see in the photograph toward the left. And finally, the master must control the thermal management system, which in our case is external to this box and must be done using external communication. One important benefit of a master-slave design is that many aspects of the design can be reused from one application to another. We don't have to redesign the electronics starting from zero, starting from nothing every time we build a new battery management system for a new application. So we ask in this slide, is it possible to reuse a slave design? And often the answer is yes, assuming that the electronics used in the slave design are flexible in terms of the number of cells that they monitor, and assuming that the physical size of the slave design is something that can fit into different packages required by different applications. Maybe surprisingly, often the packaging size, the form factor of the slave turns out to be surprisingly important. So even if the overall electronic design can be reused without any changes in different applications, it can be necessary to redesign the circuit board footprint to fit in different applications. If we anticipate that our product will have very high volume production, in that case it might be to our advantage to optimize the slave design for that particular application in order to save some cost in every slave unit that we sell. Also, you know that different lithium-ion cell chemistries have different voltages and different temperature ranges. And for example, a lithium iron phosphate battery cell often has a maximum voltage of around 3.6 volts, whereas others like NMC have maximum voltages around 4.2 volts. So if our electronics are capable of measuring voltages between 0 and say 5 volts, we can accommodate different chemistries by simple software changes that anticipate these different voltage ranges. But if our electronics can only handle a limited range, then we would need to redesign for every different chemistry. It turns out that a 5-volt voltage range is pretty common, and so it's quite easy to design the slave electronics to be able to handle any lithium-ion chemistry presently on the market. So it's often possible to reuse the electronic design for a slave board. So we ask, is it possible to reuse the electronic design for a master board as well for different applications? And it turns out this is often more difficult. The master design needs to be more flexible. Different applications require different numbers of contactors and different types of contactors. And so if we want a universal design, it has to be very flexible as to how many contactors it controls and the ability to produce the different signals required to control those contactors. The current sensing solution that we use in the battery pack also requires some flexibility because we can use fundamentally different approaches to measure the electrical current. So if we require a universal design, then our electronics must be able to control these different types of current sensor. There may be different ways to connect the battery pack charger depending on the application, and there may be different types of thermal management system as well. And so it's possible to reuse the design of a master and a battery management system, but this can be accomplished only by incorporating quite a lot of flexibility using additional analog and inputs and outputs and digital inputs and outputs that might be required in a special purpose design. So we might consider a fairly generic design that we never actually implement, but when we implement a specific design, we take features from that generic design and keep those, the ones that we require, and then we omit the features that we do not require in a particular application. This brings us to the end of this lesson, and to summarize what you've seen, you've learned that high energy and high power battery packs require cells configured both in parallel and in series. Safety and cost limit the number of cells in series, and losses versus cost give us a trade-off for the number of cells in parallel. So the overall design is some kind of an optimization between the factors of safety and cost for the number of cells in series and the losses for the number of cells in parallel. You've learned that battery packs are often built from smaller modules of cells, and this gives advantages with regard to how the modules are handled and how they're tested, and it tends to reduce the non-recurring or NRE engineering costs of building different battery management systems and packs for different applications. The fact that battery packs are often built with a modular design motivates building battery management systems with a modular design also, and it's very common to see some kind of a master-slave topology in a battery management system. The slaves handle the voltage measurement and the temperature measurement and balancing, and the master handles the battery pack current sensing, the isolation sensing, the contactor control, and thermal management. This modular design tends to make it easier to reuse the slave solution in many different applications, but there are greater challenges in reusing the electronic design of the master unless a lot of redundant components are built in to add quite a lot of flexibility that isn't usually needed in any particular application. So in relatively high volume production, it usually makes sense to have a specialized master board for every application, and in some cases it even makes sense to optimize the design of the slave board as well. But we also mentioned that the specialized electronics of a master implementation could be based off of some generic design where you keep only the components from the design that are necessary and by eliminating the components that are not necessary in that application. So that brings us to the end of this lesson, and we continue by looking at, for the rest of the week, the requirements of a battery management system to be able to measure and control components inside of the overall battery pack.